One of the notions, wow. Wow. I think we're a little too loud here. Okay. What I wanted to talk to you about is to make a thinly veiled plug for a course I'm teaching next quarter called Artificial Life, Artificial Culture, and Evolutionary Design, and to introduce you to some of the ideas and topics, many of which I think are quite relevant to you as artists, biologists, social scientists, humanists, and whatever. Since you just saw this film and saw a little bit of a reconfigurable robot, I'd like to kind of carry on in that vein. One of the things that is really surprising to my mind, which I think carries a lot of implications for science and for philosophy and for epistemology, that is to say, how we come to know, how we think we know, we learn about the world outside, is this notion of evolution. And you can think metaphorically of evolution through Darwinian natural selection, Darwin and Wallace and their theory of natural selection. You can think of evolution as the creator of us and all the other plants and animals around here. And so it's particularly significant, I think, when we, in the last 50 years, have not only built machines that arguably think, and software that arguably thinks, but on top of that, we've begun to build software that actually evolves. That is, it can adjust itself to a particular problem through natural selection. We've built software, I'm not speaking of me personally, I'm speaking of the discipline. Built software that can write itself, that is, it's software that will evolve a program to solve a particular problem. Okay, this is all in software. Wouldn't it be neat if we could build hardware that way? That is, build something physical and tangible and let it evolve by itself. That's already been done about probably about 4 to 5 years ago. Has anyone heard of field programmable gate arrays? No? If you say it real fast, it sounds like field programmable Gatorade, but don't want you to confuse it with that. They're called FPGAs, and what they are circuits on a chip. But the gates, that is the physical connections between the diodes, the transistors, and so forth on the chips are programmable. So there's a programmable layer that actually physically reconfigures the circuitry on a second level of that chip. And these things have been programmed to evolve novel circuits for what? For amusement, I suppose. The practical end of these field programmable gate arrays is this. You can, let's say you have a microcomputer, it's a PC and it runs on an Intel chip, and you've got a Mac and it runs on a Motorola chip. What if you want a new kind of computer that you give it a problem, you describe a problem to it, and the computer sits and looks at your problem and it says, gee, well, really to solve this efficiently, I need to be 3 Intel chips and 7 Motorola chips. And then, zap, it reconfigures this programmable gate array to be just that, and then executes your program on it. So that's what they mean by field programmable. And these chips have been sent to Mars. The Pathfinder robot was programmed with these FPGAs. Okay, so that's a practical application. Now getting sort of into the philosophical and theoretical end of things. there have been a couple of experiments with them, which are kind of neat. What if you wanted to evolve a circuit that acted as an oscillator, that put out a frequency of, I don't know, say 2 kilohertz or 10 kilohertz? You can program this. I'm expanding the chip for illustrative purposes. Okay, it's really tiny, but you can reprogram this thing to represent 100 or 1,000 trial circuits that are put together randomly. And you can test the outputs of these things and subject them to mutation and recombination. Fill the FPGA with, say, another 1,000 of these circuits. Test each one to see if it oscillates correctly. Pick the ones that are the best, let them be parents of the next generation, and so on and so forth. This has been done with an oscillator. It's also been done to evolve a radio to pick up signals from, not too surprisingly, the computer that was sitting next to it. So that's a pretty neat idea on 2 levels. One level, maybe you can use this to design useful circuits. Secondarily, it has an emergent property that the circuits that evolve in this thing are not really the circuits that engineers would necessarily design. They are circuits that make opportunistic use of parts of the FPGA that were not designed to do what the evolved circuit is using them for. In other words, the circuits have evolved to make use of small differences between the components on the FPGA, to make use of differences, say, in the thickness of the multiple layers used to print all of the devices on the chip. Some of the circuits evolved in such a way that the experimenter working in his or her laboratory, in the case of this evolved, well, both in the case of the oscillator and in the case of the evolved radio, the circuits would work. The circuits would be a radio or be an oscillator, but only if the soldering iron 6 feet away was plugged in and not turned on, and only if someone was standing in this part of the room, and so forth. So these are rather neat philosophically in that they're taking advantage of environmental characteristics that nobody really thought to put into the circuitry. Okay, so there's evolved hardware, at least at the chip level, and one of the current challenges is to evolve hardware at the robotic level. It would be nice to have a robot that you could send to Mars, and maybe it had wheels and it would roll along until it got into kind of a lumpy terrain, and then the wheels would turn into legs and it could walk, and so on and so forth. So that's what that reconfigurable robot was getting at. I don't have any illustrations of this, but last week there was a presentation by some roboticists, not at UCLA, but they presented at UCLA, and they were assembling robots out of, say, 10 or 20 modules that could actually, each one had some intelligence. It had connectors for to sense and send data. Each one had a pair of movable articulations, and these things could unite end to end and move sidewinder fashion, or they could reconfigure themselves into the shape of an X and elevate the central part of it like the body of a spider and walk in that fashion. One of the illustrations in the article showed these very same modules reconfigured sitting on a tricycle seat with its legs on the pedals and pedaling the tricycle. And has anyone heard of a hoop snake? No? This is sort of Western American mythology, folk mythology. You've heard of jackalopes? Okay, well, this is, if you travel It's sort of the outback of the West here, and go into service stations or bars where they've got all these stuffed critters. You'll see every now and then a stuffed rabbit with antlers on it, which is a jackalope. Doesn't exist. Hoop snake is another idea like this. If you want to scare people, you say, look out, there are hoop snakes out here. What they do is they'll chase you, and they don't slither like ordinary snakes. What they do is they grab their tail in their mouth and get up like a hula hoop and roll after you. Okay, well, the researcher who was working with these modular robotics pieces had heard of hoop snakes. He hadn't heard that they were fictitious, but again, these modular robotic pieces, he managed to program them to attach tail to head and roll along. So this is pretty well where the state of the art is in reconfigurable robotics. How much time do we have?
You can go as long as you like, but I figured about an hour or so.
Oh, okay. All right. Let's see. Anyway, I'm offering a class in the spring which will take up some of the theoretical and philosophical and epistemological ideas behind artificial life and artificial culture and evolutionary computing, evolutionary design. Let's see. We're cut off at the left edge. Is there any way to recover that? No, well, there's not too much there. Anyway, the course is Honors 69. I'm not responsible for the numbering, but hopefully you'll remember it anyway. And there is, it's going to be taught in the Click PC computer classroom in the Powell Library, room 307. I think we have room for 15 people in that. It seems to have already attracted seven enrollees, so I invite you to enroll if you're interested. You might want to do so quickly. The course is going to be based on, I guess I can walk here. If the bookstore can acquire them, these are the two required texts that I've asked them to order for the course. One is, not surprisingly, this is where the title for the course comes from. One is called Artificial Life. It's edited by Chris Langton. What it is a compendium of I encourage you to flip through some of the imagery in the Red Book. It's a compendium of some of the better articles out of the journal called Artificial Life. This is a publication that comes out of the Santa Fe Institute, which plays around with these very heady ideas. The second one is called Evolutionary Design, and it's largely about evolutionary computation and art. Okay. I'm not formally trained as an artist, but I think the artwork that comes out of evolutionary computation provides a wonderful visualization for getting across the underlying ideas in these processes. Okay, so the course is open to everyone. I would be thrilled if some of the people who take the course would be interested in doing some programming in Borland C++. It's not as hard as it sounds, but I'm not requiring that. So if you're interested in the course, please do sign up. You do not need to learn programming in the course, but if you'd like to, I'll provide you with that opportunity. And as a preview of what the programming's about, I'm doing a short workshop next Wednesday in Powell Library, again room 307, on Borland C++. It's a rapid application development system, which uses drag and drop components. So it takes a lot of the pain and suffering out of programming Windows applications. Let me just, my training has been as an anthropologist, archaeologist. I've been a museum curator, so I'm very much interested in hands-on learning and artifacts. So I brought a few to show to you today. So I'll just take a little trip over here. It's heavy, you can pass it around, but one of the points that I like to make is that computation, well, it's much more than the PCs, and you probably already understand this, it's much more than the PCs and Macs sitting on desktops. The modern period of computation probably can be tagged with more or less the year 1950, but there are a lot of mechanical computing devices that preceded the electrical computing devices, which preceded the electronic ones, which preceded microchips. And there's a lot of experimentation going on now. And have you discussed DNA computers? Okay, I don't mean metaphorically that DNA can compute. I mean people who've actually taken DNA and RNA and encoded a combinatorial problem into strands of DNA and then subjected it to replication and selection in literally flasks of fluids to have it solve a combinatorial problem like the traveling salesman problem. Do you all know what the traveling salesman problem is? I think maybe we should rename it the concert tour problem. It's, let's say you're a band or a rock group, you've got 25 cities you have to hit, and you're traveling by bus. What's the shortest path that includes all the cities without going through the same city twice? It's a problem that's very easy to solve when you have 5 or 6 or 7 cities. It's a problem that becomes computationally very difficult when you have 10 or 20, and as it grows up to 100, it becomes virtually impossible to solve directly. So this is the kind of a problem that can be solved by DNA computing. There are also evolutionary computing techniques on standard machines to do it. So at least in this course, I'd like to get people familiar with, how many of you do programming? Okay, in, let's say, C++, how many people have done C++? How about BASIC? Fortran, HTML stuff, Microsoft Word, oh wow, okay, Excel, stuff like that. Okay. So the idea is that computing can take place in a lot of different media. A lot of pioneering work is being done with DNA computers, and there are a lot of people trying to figure out how to do it, how to build quantum computers, which I don't thoroughly understand enough to explain to you at the moment. But I'd like to kind of back up to the 1950s. Anyone here ever play with a slide rule? Anyone know what a slide rule is? Everyone. How many people have picked one up and slid it around? Okay. How many people can actually use it? Hooray, me too. Okay, so that's an analog computer and it's a mechanical computer. It doesn't do too much. Here's something that looks pretty terrible. Actually, this is a mechanical computer. It was used to compute the latitude and longitude of aircraft in the 1940s and 50s. There are two inputs to this. I can't quite see them, but there are two cables that come into it that spin around. One spins around proportional to the speed of the plane. And the other one turns proportional to the direction that the plane is going. So I'm tweaking the gears in the back, and you notice the compass direction is changing. And if I tweak the other gear, you probably won't see too much happening, but actually this is the air speed indicator. And what it's doing is actually using trigonometric functions to calculate the position based on the speed and the direction. How many of you have had trig? Everyone has, okay. So basically your position north is going to be your distance at a certain bearing times the sine of the bearing angle, right? And your easting, or position east, is going to be that times the cosine of the angle. So they're actually, well, don't drop it. Whoever doesn't want to carry the thing, that's fine. You can tweak the gears on the back, but what's in here that's very interesting is that it can compute sines and cosines and also integrate them, that is, accumulate them, using a series of rollers, spherical balls, and discs. So you can do an awful lot of programming just with mechanical components. I found that in a junkyard just last week, which was kind of neat. So you can start with that kind of a thing. Clearly, PCs will do it a lot more quickly. I don't know, which one is better, do you think? Depends, yes.
Can you get a lot of error propagating with this?
Pardon?
Can you get a lot of error propagating with this?
Considering, probably not too much, given that the inputs are correct. Sure, there's a certain margin of error, and you can probably compute a lot more detail, but I think it was pretty good for what it's designed for. If planes are flying, well, this works without electricity, which is nice. Your computer won't. Okay, let me show you something else here. So what was the impetus for designing modern computers? If I say they kind of appeared during the Second World War in the 1950s, why? Who was paying to develop them? Pardon? I'm sorry? Cryptology, okay. Specifically what? Who was trying to decrypt whose messages? Everybody, I guess. Okay, so the Japanese were sending messages by code, and we were trying to decrypt them. We were sending messages by code, they're trying to decrypt them, but the main impetus came from trying to decrypt German codes encoded with the Enigma device, which you've probably heard of. What's that submarine movie that's recently, a year or two? U-571 or something? Yeah, okay, there's some scenes in there with a real Enigma device. So that was really the impetus, and that device you can consider to be an early electromechanical computer. This was also used during the Second World War. This is please don't drop it. This one is quite scarce. This is called an M209, which should give you an idea of the rapid development. This is absolutely purely mechanical, and it will encode, not terribly securely, messages. And the impetus for the building of computers in Britain to decode the Enigma devices was a combination of mechanical devices and electromechanical devices in racks and so on. Yeah.
Can I just make a comment on cryptography?
Mm-hmm.
Last week, it was announced that a company here in the United States has genetically engineered a chicken to have larger breasts, and they're going to put a DNA encryption key in the genome of that chicken so that they can track what growers are using their genetically enhanced.
This is sort of a copyright notice inside.
Copyright notice that's encrypted in the DNA.
Mm-hmm.
So it's just amazing, this notion I mean, imagine going from this and those purposes to now intellectual copyright of biological work.
Right. And what was current high-tech, this was sort of low high-tech during the war, but I'm sure people would have killed at various points to have it. Now ends up on eBay some 50 years later. Okay. And just, has anyone heard of core memory? What is core memory? Right. Well, okay. That's what it is to you. Has anyone else heard of core memory? You're absolutely right. Core memory is usually, if anyone has heard of it recently, it's considered to be the main memory in a computer, but the term core harks back to the days when the memory in a computer was, as you all know, it consists of binary digits, bits, okay? And one bit of information would be stored on a little bead, a core, either by magnetizing it north in this direction or north in that direction. So memory was built out of this stuff. Here's a trashed example of a core memory. This is probably about maybe 1 megabit of core, and you think about your computer chips now. But if you look at this, it has about 30 planes, and on each plane there is a network. It's like Windows screen, and at every intersection of the wires there is a core. And so this was a device to store magnetically data and programs. I'll pass it around. The surface of it has been trashed. I just didn't have time to excavate it to a pristine one. But you can see on the top the copper-colored wire which has been torn. There's a little loop at every intersection. Thank you. So is this stuff totally obsolete now? Does anyone know about this? It's still used. Where would you expect? Technologies don't necessarily become obsolete. They become very specialized. This is still used in the space shuttle, mainly because cosmic rays do nasty things to microcircuits. So this is very reliable. It's also used in military aircraft, where someone who designed them figured that they're going to survive a nuclear attack. When a nuclear weapon goes off, it creates an electromagnetic pulse which will fry computers for miles and miles, but it won't fry core memory. And here's sort of the last example of this. Here the cores are the size of vitamin pills, and this is actually a program written by threading wire either inside or outside of a core to represent a 1 and a 0. So here you have about 500 wires hand threaded through about 30 cores to store a program. And that's pretty difficult.
Is that still storing the program?
Pardon?
Is that still storing the program?
Yeah. If you look at the end, it'll say, I don't know, it says program 036 version 2 or something on it. And those things were all threaded by hand. So we've gone a long ways. These things are still in use, so I think even if you put your wildest imagination to what's going to happen 10 years or 20 years down the road, you'll probably be conservative. And I expect you've all seen, so there's the core memory. You can actually see the bits there. This is a silicon wafer on which about 100 chips have been formed. They've been tested. The good ones have been saved. The bad ones, someone's painted a red dot on each of them and thrown it away, and this is the throwaway. So again, kind of another interesting aspect to chip manufacture is the percentage of rejects. You just print these up en masse, you test them, and this is about a 50% rejection rate. Has anyone not seen Jurassic Park, the movie? Oh, okay. Those of you who have seen it, do you remember the computer in Jurassic Park? Yes. What was it? Was it a prop? Was it real? How many say it was a prop? How many say it was real? How many don't know? Oh, okay. Actually, yeah? I'm sorry? In the first Jurassic Park, no, well, there's one main computer. It's black, and it's like 3 or 4 vertical slabs with a whole bunch of red LEDs, lights blinking on it. And they talk about it. They keep saying, oh, well, our connection machine 5. Pardon? No, they refer to it as a connection machine made by Thinking Machines Corporation in Cambridge, Massachusetts. It is and was a real computer, a supercomputer made by this company. That's probably the biggest public display of their product that was ever accomplished, and it's one of the fastest supercomputers in the market. They've unfortunately gone bankrupt, but... Pardon? It's called Thinking Machines Corporation. So, and here is a processor board out of that machine. So this has got 8 CPUs on it. It's very likely that the complete machine, the CM5, had several thousand. The precursor to that, the CM2, came with 16,000 microprocessors in it. And the CM5 was an improvement, and again, if you want to pass that around and have a look, you can get some kind of an idea of where the technologies come from and gone to. Yeah. Yeah, right. See, just having been a museum curator and archaeologist, I just can't help having these things. And
I asked him, are these your personal collections?
And I said yes. We're 2 museums in British Columbia, which had nothing to do with technology, but it's stuff that you don't usually see, and I think it's worth kind of getting your hands on them. Okay, I'm going to stop pretty soon, and hopefully you'll have some questions we can talk about and discuss. Anyway, very. Yes, I'll do that. Okay. So I've taught several courses along these lines, but the one coming up in the spring hopefully will be the best because I've learned from my mistakes, and it's an honors course. There are going to be a lot of bright people. Hopefully you bright people will join it. And we've gotten more and more equipment. One of the things that will be, or you'll have an opportunity to play with, has anyone played with these guys, these devices? These are Lego Mindstorms robots, okay? They're actually developed by the MIT Media Laboratory. And the development started on these probably five to 10 years ago. Charles Taylor in the biology department had his students building these devices as simulations of primitive life forms, as bugs and bacteria and so forth. What this is a microcomputer in a brick. It's a microcontroller. Other people will refer to it as a microcontroller. It has 3 inputs and 3 outputs. And it's completely programmable on a PC or a Mac. So you can program this in a jigsaw puzzle kind of visual code, or you can program it in C++. And it's interesting to see, well, let me turn one of these on. One will work, the other one won't. Okay, so anyway, this one is programmed to, if it hits something with its right bumper, it backs up and turns left. If it hits something with its left bumper, it backs up and turns right and otherwise wanders around. Okay, so it's an interesting way to experiment with computer programming, but with a real-world interface, okay? The PCs that we have here, what do they know about the world? They only know what keys you press and where the mouse rolled, okay? This is a much more primitive CPU, computer chip, but at least you have 3 real-world inputs and 3 real-world outputs. It can input information, for instance, go ahead, yeah. From each of the 2 feelers, this one has an infrared emitter and receiver. So the sensors on it, the inputs, can be a variety of things. You can even put pH probes there. Temperature sensors, humidity sensors, you plug all that stuff into them. I imagine you could build a rather neat interactive art project. Well, let's see where it goes. Or anyone who wants to pick it up and pet it or play with it or rip it apart, that's fine. This one is programmed to follow a line, and I wish I could show it to you, but someone has erased the program. So, but anyway, it wanders around and follows a line. Let me ask you, how would you program a device like this to follow a line? Here's what it has. It has an infrared emitter and detector. So the only thing it's sensing about the world is whether what it sees is black or what it sees is white. And it has 2 actuators, 2 outputs, a motor for the left wheel and a motor for the right wheel. So how could you get it to follow a line? Simple way. This is kind of getting at the question of, well, really, how intelligent are these things, you know? And kind of the key question after that is, how intelligent are we? We think we're really smart, okay? We think we're doing a lot of thinking, but maybe our consciousness isn't really making the decisions. Maybe the decisions are coming up from very, very primitive, very simple, evolved mechanisms, and our consciousness is saying, "Oh yeah, I knew that. I knew why I did that," but it really doesn't. But back to this simple, yeah.
Shoot out the beam, and whichever side it feels a lack of black, if the line is turning to the left, it'll see less black on the right side and just speed up that side.
Okay, that's a way to do it, but is there a simpler way? This beam is shooting straight down. Okay. See, we're not used to thinking about simplicity. If I tell you this thing follows a line, and if I laid it out and it followed it, the natural reaction is to say, oh, gee, this is pretty smart. So I'm trying to get you to tell me a real stupid, dumb trick that this can use to follow the line. No? Here's one hint. The line's thick.
Well, probably if you read black, move forward as to right or left until you see black again.
Okay, you're right. You're right on. A little modification of this. If it sees black, make the right wheel turn. If it sees white, make the left wheel turn. Simple as that. And so it'll wander along one edge, going back and forth, and so forth. Pardon?
You can only go one way along the
Right.
program, but you go the other way around.
Well, if you turn it around to the other direction, it'll feed off the other side of that line. And because it's embodied, because it's got actual physicality in the certain turning radius and things, there are certain curves that it can follow, certain curves it cannot follow, and there's a lot of experimental psychology that can be done on some simple stuff like this. Okay. Let me just show you. So if you're interested in the course, there is a syllabus here. There's a calendar which basically shows the progression of ideas that we'll be entertaining. And I won't go over that because you can read it. Let me just switch to a page of applications which will give you an idea of the kinds of things some of the participants in these courses have done over the last 3 years with Borland C++. And basically the courses that I've done, half the students have never programmed anything before. Everyone ends up programming. It's not that hard, okay? In fact, the programming environment that we have, what I tell everybody to do is ignore 98% of it. You know, we're only going to deal with a very small part of the Borland system, and we're only going to deal with a small part of the C++ language, enough to enable us to do some simulations. So here's some simulations. This is intended to demonstrate, I can't reach it, that's all right, emergence. I don't know if you can see it, but there are three, it's quite similar to this program. There are actually 3 yellow dots which define the vertices of an equilateral triangle. And here's an interesting problem. The problem goes like this. Pick a point at random, and if I can click on the screen, you may see a dot there. Believe me, there is one. And then I can pick a corner at random. And what the program will do is draw a line from that dot to the corner that I picked, and then pick a new dot halfway between them. From that point on, the program is just going to pick a corner at random. Well, let me click next here. Well, it picked the same corner, and it drew another dot halfway to that corner. Now it's picked the top corner, and it's drawn another dot there. Okay. So there's a lot of randomness in this. Okay, you can imagine trying to do this by hand if you're sitting back 100 years ago and with nothing better to do. The question is, will anything interesting ever happen? What are you going to get? Pardon? Somebody said something. Oh, okay. Any other ideas? I'll keep clicking here. Oh, click the wrong thing. Oh well, that's what you get. Would you have been able to predict that? So in a certain sense, with emergence, there's really no way to predict the outcome of simulated worlds other than to actually run the world itself, to execute the command itself. So this is a program that's very easy to write. Some of the participants wrote other versions of it. Here's another version someone else wrote, which does the same thing. Then another participant asked, well, what happens if it's not just an equilateral triangle? What if you make it into a polygon of some sort? So, okay, here we can set the number of sides. You may not see the corners, but we can run it. With 3 sides, it looks like that. We already knew that. With 4 sides, what are you going to get? Pardon? Squares. Anyone say anything else? Okay. So not only can we intuitively not really predict the triangle situation, but based on the triangle situation, there's no clear path to intuit the 4-sided situation. What about 5 sides? I didn't mean to discourage you. No, you can be optimistic and say we get pentagons. Okay, so you get something like that. Now this thing plotted so quickly, we've got points being plotted over the top of other points, so we really don't know what the topography of that is, right? I mean, you know, maybe there are other pentagons. If we could see this in 3 dimensions so that the points all stacked up, something interesting might happen. So we can actually render this whole thing in gray according to how many points are in each space, and we get another rather neat emergent pattern. We can render it in color. And then we can say, well, okay, the red points, this is where there's a lot of stuff going on. And in fact, if we could render this as a topography, what you'd see is that there are really sharp points up here, but most of the land surface, most of the topography is very low. So what we can do is actually cut down the scale that's being plotted here and get a visualization of the lower topography there. So one of the class participants suggested the polygon approach. Another participant helped him debug some of the program, and I thought, well, gee, at that point it just plotted in blue, and I thought, well, why don't we see this in color and see what's going on. So this code is, I won't bother to explain it to you, but the source code for all of this stuff is here. We don't really have time to go over it, but it's there for anyone to copy, and none of it is very long. I think maximum 1 or 2 pages. Has anyone heard about cellular automata? Cellular automata? Does it ring a bell with anybody? Conway's Game of Life? No? Oh, cool. Okay. All right, I'm going to turn this off. I know I'll step on it, but maybe I won't. All right, here's an example. All right. This is a cellular automata program, and a cellular automata is a certain class of artificial world with the following properties. It consists of cells, like squares on a sheet of graph paper or squares on a checkerboard or chessboard. The cells can have different states. In this case, a cell can be either green or red. And metaphorically, in this case, we're going to say, if it's red, we'll call it dead, and if it's green, we'll call it alive. All right. And this is what, if you can imagine this as one frame, the beginning frame in a movie. Okay, movie film, I guess you've seen it, it's just frame after frame. And what we're going to do is compute the next frame in the movie based on the state in frame 1, that is, whether the cell is dead or alive, and some simple rules. And the rules are more or less as simple as this. If you're dead, And in your immediate neighborhood, that is in the 8 cells around you, there are 2 or 3 cells that are alive. You will be alive in the next frame. And if you're alive, if there are not exactly 3 cells in the neighborhood that are alive, you'll be dead in the next frame. Okay, simple rules. What happens? Anything interesting? I mean, if somebody came up to you on the street corner trying to pitch this to you, what would you say? Well, I don't know. The intuition is that probably...
Does it have to be some sort of shape? Because all the live ones are going to try to stick together. They all...
well, let me just show you. There are lots and lots of cellular automata rules. Okay, the one that I gave you, I may have the numbers off 1 or 2, but it's as simple as that. There are other rules that are more complex. There are other cellular automata systems where you have 10 states or 20 states, 10 or 20 colors. So there are a lot of variations on this theme. This particular variation is called Conway's Game of Life, and this is what happens. Again, philosophically very interesting, I think. It's an emergent system. You seem to get different species of configurations. Yet there's nothing programmed into the system that says they're going to be squares, they're going to be delta things, they're going to be flashing crosses. None of that is programmed in. It all emerges. And I think most of us would say there are objects here. There's a hot dog shaped thing. There's a sort of a cropping thing from Photoshop. There are objects of different kinds. So what's the origin of objects? Where do these things come from? With this program, you can also stop things and draw a particular shape and, oops. And step it to see how it evolves. That step, that particular shape just fades into oblivion. A lot of work has been done with this system to try to discover the total range of species of creatures that emerge from it. Here's a variation on that program done by another participant. You see the same kinds of things happening. But you notice that there are objects that actually travel across the screen? I'll wait till most of this dies because Simone added a button which will create a configuration that actually stays intact and moves across the screen. So actually, let me kill everybody and then I can add a creature. And if I step through it, this is how the configurations change. So actually a cellular automata system can be made to imitate almost any system that you can think of. The class ends at 3:30? Or? Oh, okay. So you can envision these are 2-dimensional cellular automata. There are also 1-dimensional ones, 3-dimensional ones. You can envision 4-dimensional ones. There's a physicist by the name of Ed Fredkin who operates out of MIT who who has claimed to be able to represent all the laws of physics in cellular automata systems. That is, by defining a set of rules, defining a grid in states, he can simulate all the interactions that you see in physics. And from that ability, he has made the claim that, in fact, the universe itself is, in some sense, a giant universal cellular automata computer, and all the things that exist in it, all the laws, all the objects like us are actually programs running on this computer. Now, at first hearing that may sound kind of absurd, but if you think about it and think about the notion that, okay, these objects really have no knowledge and can have no knowledge of the system they're running on. If we kind of extend that notion with us trying to imagine the quote-unquote universal computer that we're running on, I won't say it's impossible, but it's difficult. Anyway, it's an intriguing idea, and well, Matrix plays around with this idea, the film. You've all seen that? Has anyone seen The 13th Floor? Okay, I think it's much better film. It's very subtle, and I usually assign that as a paper topic for people to look at the film and take what they know about computing and do a critique of it based on that. Anyway, I recommend the film to you. This course wasn't necessarily designed. Most of these courses were taught through the social sciences, so they were not really designed for producing programs of artistic merit. So those of you who are in design and arts, don't think you need to be constrained to this. You can probably do a lot of very novel and very complex programming with the system. This is a fairly simple simulation. It starts out with 4 agents, 4 dots, who are called Bob and Carol and Ted and Alice. And the story behind this is that Bob really likes Carol, but Carol likes Ted, and Ted likes Alice, and Alice likes Bob. So they're really kind of chasing each other in a circle, and it's just a simple simulation to illustrate the path that they would take if that were the case. Okay. And we can change Bob's level of attraction to Carol and Ted's level of attraction to Alice. Press to clear the screen. Disperse moves them back to the corners, and then let them chase each other again. So what you see here is really a composite of a number of different variables for attractiveness and the resulting pathways. Here is a more elaborate version of the same thing. And it starts with several hundred individuals, so I can plot them on the screen as dots. And what has happened here is that we've got 2 things going on. We've got attraction and avoidance. Each individual, each dot here, and I'm going to start calling them agents, each agent here is randomly assigned another agent that it is attracted to and another agent that it is unattracted to. So it'll try to move towards one other agent at random and try to move away from another agent at random. So what's going to happen? Well, they kind of form this sort of flocking behavior, which seems to result in kind of an orbiting behavior. They move apart, so I can keep zooming out to see what's going on. I mean, this could be the basis for some crowd scenes in a Hollywood film. Did anyone see the Batman film with Danny DeVito as the Penguin? Okay. Is Ruth? Where'd Ruth go? Oh. Did you show them the Nightline video? Not yet. Okay. Well, you'll see an example of similar sort of simulation which drives the penguin scene in that film. There are hundreds of penguins wandering around, and their locations are programmed with a similar sort of simulation. So let me reset this. Stop it. Let's see. Plot it again, and let's show the tracks of these individuals. Okay. Now, why would I be interested in this as an anthropologist? Because abstractly, if you translate the space here into a conceptual space, there is probably some relevance here to group formation, to the separation to the formation of different cultures, subcultural groups, and so on. So there's a plot of simply the tracks, and I can turn on a probe here, which actually will pick one agent at random and draw a, whoops, where are we? Pick one agent at random, which is, can't reach it, which is this agent. And it progressively will draw a green line to the other agent that it's attracted to and a magenta line to the one that it's repulsed from. So it's a way to visualize what's going on. There's a big challenge here. How do you visualize the entire interactions? If I tried to plot all the magenta green lines for all the interacting pairs, I wouldn't see anything. So how do you come to grips with the kind of behavior that emerges from these systems? How do you capture it in a visualization? It's another interesting problem. And let me show you a very simple simulation. Can I save stuff anywhere on this? I guess so. Temp F, all right. Okay. Okay, I'm going to fill the world randomly. So here's a cellular world that's 500 by 500 squares, and what I've done is to fill it randomly with three kinds of individuals. There are red ones, there are green ones, there are blue ones. And a quarter of all the spaces are filled with red individuals, a quarter with green, a quarter with blue, and the final quarter is empty space, which is plotted as white here. And this attempts to get very abstractly at some questions about segregation in social science. What would happen if we have a small level of prejudice here? That is to say, what we're going to do is we're going to pick a space at random as a source, and if there's nobody there, we'll pick another space. But let's say we find somebody there and it's a red individual. And then we pick another space at random, which is a destination. If there's someone there, we just skip it. But let's assume that we get a red individual here and an empty space as a target location. What the program is designed to do is to say, okay, I'm red. There's an opportunity to move into this white empty space. Let me count the number of neighbors that are like me. And if there's one neighbor like me, I'll move, one or more. If there's not any neighbor like me, I won't. So if the level of selection or prejudice or whatever you'd like to call it is one, and you let this run a while, you begin to see a little bit of clumping of individuals. Let me crank it up to 2. At the level of 2, the clumping starts to accumulate much more quickly. If we crank it up to 3, I believe that's where the maximum segregation occurs. So there have been variations on this way of imagining the problem that social scientists have worked on. This again is very abstract, and I wouldn't want you to make any social decisions based on what this little simulation does. Another thing which you can do with this software is to open up an image. You can create an image in Photoshop, which is a nice way to render data. In this case, what I've done here is to create this pattern, which really is a representation of regional differences in the desired number of neighbors like yourself. Okay, so in the white areas here, there's a very high. You will move to that location only if there are a lot of individuals like yourself. If it's a black area here, there's no prejudice in that sense. So what this is trying to get at the question of what extra influence do patterns in space, or might patterns in space have on the segregation problem. So I can create any sort of a map in Photoshop, import it into this program. I can now, let's see, fill the world with individuals at random and draw it on the screen. This last button here takes that image as a BMP image and translates it into something that the program can read. And if I click the little box here, it has the effect of turning off the slider bar and making the decision about how many desired neighbors one needs to move to that location based solely on the geographic differences represented in that black and white image. And if you let this run long enough, you get some very interesting things. For one thing, you can begin to see how the number of desired neighbors affects the nature of the clumping that you get here. You'll also see that in these areas where there's a low level of desired neighbors like oneself, they become depleted. And you begin to see some boundary effects which tend to be subtle. That is to say, if you let this thing run long enough, you begin to see a white area of vacant land forming around some of these clumps. Okay. Again, it's very abstract, but with some tweaking, you might be able to make some quite valid social predictions or some theoretical examinations. And let me just show you one more piece. Two more pieces. One of the participants in the class decided to turn this into a somewhat aesthetic project. Instead of using just 3 colors, this person decided to use the whole gamut of the color spectrum. So how many colors does Microsoft Windows support? Lots, okay. All right. 256 times 256 times 256, I think. Okay, so he decided instead of using 3 colors, what he's going to do is create colors at random with red, green, and blue primary color values that range from 0 to 255. And the agents will move towards areas where the neighborhood is similar. Now, at this point, this probably departs a lot, well, maybe not. I was going to say it probably departs a lot from social science theory, but it may be getting at some other aspects of social selection. If we talk about education levels or certain communities that attract like communities, there may be some relevance here, but that was not the intention. So if I can fill the grid, let me see if I remember how to get this thing to do something interesting. And if you're going to ask me what fixedness is right now, I'm going to tell you I really don't remember. But the source code is there. You can go and figure it out. Anyway, it does something rather interesting, and we really never spent the time to analyze what was going on. Okay. So there are some rather unexpected things that can come out of these simulations, some of which may be relevant to art, some of which may be relevant to social science. All of which I think are interesting in some fashion. Here's the last one that I'll show you, and this is a growth algorithm, and what you have to imagine here is, okay, I'll empty it and render it. So here is a two-dimensional space. And the idea is that from one of the edges, one agent is introduced at a time, and it wanders at random. And if it comes up against another agent that is stationary, it becomes fixed to it. Once that one becomes fixed, another agent wanders in at random, and when it hits one, it becomes fixed. So this is a pattern of growth that you probably see in nature quite a bit. It's a pattern of growth which, if we included transportation, ease of transportation in a geographic map, it's a pattern of growth that you might see in city formation. Okay, let me see here. All right. Okay, so if I click on the screen anywhere, I'm planting a stationary seed, and other seeds will grow from it. And they're colored according to a time sequence, that is, whether they come in early or late. If they come in early, they're the white magenta end of things, and if they come in late, they kind of go to the green, blue, black end of the scale. And so you get some rather interesting aggregations here. I can also show the path that each individual agent is taking. In this simulation, you don't see the agent. It's only shown on the screen when it stops. But in an effort to debug the program, and in an effort to see what the pathways are, to see whether the wandering is actually random, there are a couple of other features that have been added to this. So let me stop it and empty it and click Show Path. And color path. Oh. Okay, agents are wandering here crazy, and they're never stopping because I haven't planted any seed in any location. So let me plant one. So like every second or 2 seconds, you see this kind of wipe go across the screen. That that separates one agent's path from the next one. So what you see here is the path of an agent, and again it's colored beginning at white for its first steps in the path and going through the color spectrum and ending at blue for the end of the path. When it becomes stationary, that path is wiped out and you begin to see the next path being shown on screen. I don't think there is a step function. Oh, there's not a step function. Okay, so it runs this fast, you can't slow it down, at least in its present form. But the visualization confirms, or it really looks like the pathways are random, so it confirms that aspect of the programming. Okay. So with that, I think I'll stop talking, and I encourage you to explore the website here. There are lots of applications.
So this is what we would do in the software teaching?
Here's the schedule for the class that I'm teaching. It's based on readings and discussions in the two books. So the main part of the class is based a lot on discussions, but there is also a class project, a term project. And anyone who would like to pursue programming, you can do that. In fact, if you'd like to replace some of the interim challenges with programming challenges, that's fine. If you really hate programming and don't want to deal with it, that's fine too. You can succeed quite well without it. So basically, I want to be flexible enough that I can stay within this general framework with everyone in the class and yet allow you as individuals to explore the parts of this that you find interesting. In a certain sense, the course is experimental. It's the first time it's been done under honors, and so we'll see where it goes. And hopefully this will become part of a degree granting program in complex human systems. So there are plans to make this, to turn this into a three-part course which will include programming, but this go-round of it is it's experimental. We'll see where it goes and try to work with who's ever interested in taking the course.
A little bit about the evolutionary, how you look at the evolutionary aspects and talk a little bit about the concepts.
Okay.
Like that topic, your evolution is not as creative agent, and that would be of interest to many other people.
Right.
So think about how you
Okay. I'm thinking very quickly of whether I can find a live evolving art project on the web, and chances are about 50% that the one I'm thinking of is not working. So let's discard that. But no, it's I think it's called live interactive art. Okay. What I'm particularly thinking of is an evolutionary program. Let me kind of visualize it for you. If you can imagine sort of a tit-tat-toe grid so that you've got 9 versions of something there. What this program does is interactive genetic art, international interactive genetic art, something like that. What the program does is to display on the web 9 abstract computer-generated shapes or designs. And what the user does is look at this and vote on each one of them. I like this one, then I give this one a 10, this is a 3, this is a 2, this is a 9. And they submit their vote on the web. The host computer accumulates these votes over the period of a day and uses them as coefficients of selection in a Darwinian sense. It says, okay, this rendering got a real high score, and this one had a high score, and this one had a moderately high score. The other ones were kind of low. So we'll take those three and we'll use those as parents of the next generation of computer programs that will generate more artworks. And so what you do is you recombine the computer code that generates these three selected individuals. So you're doing sexual reproduction here. Lots of variations on it, okay? So this is could be bisexual. Well, you have sex between two individual artworks, okay? They're not male or female, but you pick two, recombine, mate them to produce some children. There are people who've done it where you recombine from three, and in actual fact, genetically, maybe you've talked about it, there are examples of children born with genetic components from three parents. But that's another tangent, so it's not totally ridiculous. Okay, pardon?
Are you talking in the artificial life?
No, I'm talking about real life. Or you take nuclear. Oh gosh, my. Okay, what's the DNA that's in a loop in a human? A circle. Right. Okay. You take nuclear DNA from a mother. You take mitochondrial DNA from another mother. You mate that egg with a sperm from a father. You've really got now three different parents. Okay. I don't know how far in reality anyone cares to go past that, but that's been used in genetic therapy to obviate the problems of certain genetic diseases. Anyway, back to the art example. People keep selecting artworks. Over days and days, the art becomes extremely complex and elaborate. There is
I think it's called most wanted paintings, isn't it?
It could be. The one I'm thinking of is not called that.
America's most wanted, the painting that is the result of this experiment was.
Okay, the example I'm thinking of is not called that, but there are probably a lot of these things that exist on the web. Several years ago, we had a conference on artificial life here at UCLA, and I curated an exhibit of artificial life-based artwork. So that was several years ago, and you might be interested in perusing this. Some of the links probably are no longer working.
We have a link to this on 2 weeks ago, our session page. I showed them a little bit.
Oh, okay. Anyway, I was hoping I'd find the International Interactive Genetic Art page. That's the sequence of terms. Okay. Yeah. Apparently it takes up server space and it takes up computational room, and when people aren't interested in it, the administrator tells the author to take it down, and then people object and it gets put up somewhere else. Anyway, the very interesting forms or new methodologies of computation, evolutionary computation, is something we want to take up in this course, and I hope if you participate in it, you'll try to grab a hold of the whole gamut of ideas on evolutionary computation and apply it to whatever your major might be, whether it's genetics or art or social science or humanities or whatnot. There are implications for all those fields. But you've heard of genetic algorithms? Okay, this is one of the early methodologies of evolutionary computation. It's based on a very close analogy between biological genetics, chromosomes, reassortment, crossover, recombination, and computer code. There's a very close match between the two of them. There's another branch. So basically you're evolving computer code at the metaphorically genotypic level, and you're observing the phenotypic result. Selection takes place at the phenotypic level. There's another branch of evolutionary computation called evolutionary programming, in which the proponents have said, well, that's great. You can base evolution on a biological metaphor, but why bother? This is a new medium. This is computation. We don't need to do it at the genotypic metaphorical level. We can do it at the phenotypic level. So there's another bunch of researchers who've done evolutionary programming basically on the whole organism, the whole computer code. Probably the newest branch of evolutionary computation is something called genetic programming, in which you actually take the statements of computer code and represent them as a branching tree. And you actually take those trees as, again, using something of a biological metaphor, take the successful ones, the trees that produce code that does what you want it to do. You take, say, two trees, two parental trees that are pretty good, they have high fitness values, and in something equivalent more or less to crossover, you pick a junction point on one, pick another junction point on the other, and you cross the code over from one to the other. And there's some mutation variables that take place in there. There are some possibilities for replicating two examples of a branch of a tree and so forth. And this whole field is called genetic programming, and it enables you, or it enables a person to actually have the computer figure out a program all on its own. John Koza at Stanford University has really been the proponent of this field, and he's had people say, well, you know, professional programmers quite often will say, gee, you don't want to use this evolutionary computation techniques. Any programmer who's any good can write a program. You don't want to leave it to this evolutionary nonsense. To combat that, and the critique is that, well, you can evolve these things, but they'll never do anything unexpected. They'll never do anything creative. There's no originality there. John Koza decided to argue against this by evolving electronic circuits, and the ones I was talking about before are really very simplistic ones. The circuits he's talking about are complex ones, evolving electronic circuits to perform certain tasks, and then judging the outcome of the evolution of the circuit, that is the final evolved product, the final evolved circuit, determining objectively whether that is original, whether it's a contribution to engineering or technology. And the way he did this is to evolve circuits and compare them with patents in the patent office. So he's using the patent office as an arbiter of whether something is original. And this was probably a couple of years ago. He evolved, about 8 or 10 different circuits that were either patented in the past, that the computer had evolved on its own, or that were improvements on patents that had already been granted, or that were original circuits that he felt were patentable. So this, in a sense, becomes a new Turing test for Turing's test was whether a computer had some form of intelligence. Okay, this is a COSA sort of a Turing test as to whether evolutionary computation, or more specifically genetic programming, can produce something equivalent to or better to contemporary engineering practice. Okay.
But it's just not downloading. Oh, here's
Oh,
part of it. This is one
okay.
of those images from such genetically, when you
Right.
run for it.
Okay. So I think I've talked long enough. Anybody have any challenges or critiques of movies, AI, 13th Floor? Haven't seen either one?
What are some of the other movies that you mentioned? Matrix
Well, I don't care too much for Matrix. As far as the technology goes, I couldn't really. The notion there was that some computers were using humans as an energy source, which just makes no sense to me at all. So, anyway, too many special effects. Special effects were cool, but I was kind of interested in the content. And Dark City is a film that I find quite interesting. My particular interest is in what I call artificial culture, that is, creating simulations of societies, the point being to try to theoretically study the origins of society. What kind of what are the minimum kinds of functionalities that are required in order for a society, say, of 30 hunters and gatherers to begin to form social organizations of one kind or another. So that's kind of my background to it. There's a science fiction writer, a Polish fellow named Stanislaw Lem, who wrote a wonderful story back in 1972 called Non Serviam, in which fictitiously he does this on a computer. He creates entities that form societies, they learn language, they begin to talk, they begin to discuss philosophy, they begin to question whether they have a maker, and whether, if they do have a maker, they owe the maker any allegiance. Okay, this is Lem's story. And presumably the scientist who has done this didn't get his last NSF grant, so he has to pull the plug on this society. And so the story is really a question about the ethics of doing this kind of research and pulling the plug on it. So the movie Dark City is, I think, one of the first films, Hollywood films, that I have seen that takes up this notion of building an artificial society and experimenting on the inhabitants. Okay, there are a lot of artistic compromises to what I've just said, between what I've said and the way the film actually reads, but the story in the film is that some alien species has kidnapped humans, and they can rebuild the city any way they like to, and they can take what's in the humans' heads and empty it out and reprogram the humans' heads. So in a sense, it's the kind of experimentation that I'm interested in doing in social science, and I know a lot of other people are interested in doing in social science. 13th Floor kind of examines the notion of, without giving away what goes on in the film. 13th Floor, it was kind of invisible. It was never reviewed. I kind of remember when it came out, it said question reality, and it was sort of came out advertising along with the X-Files programs, and that killed it for me. I didn't want to see it. But then I rented it much later, and I find it's a very low-key but very, very rich film in examining some of the issues about the inhabitants of simulated worlds. And if you do see it, it's gotten some terrible reviews. People saying the acting is awful. But the reason that they say the acting is awful is because they don't understand the story, because you don't understand the story until the last 5 minutes of the film. So in a sense, the acting makes no sense up until the end of the film. By the time you get to the end of the film, you've forgotten all the nuances of the acting. So what I recommend is see the film once, find out what's really going on, and then knowing what's going on, knowing what's in the heads, with your knowledge of what's at the end of the film, you can start to begin to imagine what's in the heads of the actors at the beginning of the film. And then the acting makes sense.
I think we have one more question for you from here.
Okay, yeah. That's nice. Yeah, uh-huh.
What did you think and how far away is that? You must get
How far away is that? I don't know. I don't want to even guess at that. There are people who are more involved in that sort of research than I am. I think it's a real possibility. I mean, just think of Bicentennial Man has got Robin Williams as a robot who becomes sentient and tries to find a place in society, and it's all the issues about whether we should grant human rights to a sentient being that's made of silicon instead of carbon. Short Circuit, the movie Short Circuit, takes up that same idea, but it's much older. There are a number of films that take up the idea. You know, how much of our decisions in society are already being made computationally? Is the way I would sort of reframe the question. I think this synthetic sentience is creeping in, and it's all around us, and we don't really pay much attention to it. When you start thinking of John Coase's evolutionary programming, creating patentable devices, you know, what happens when you get to the state that you turn your computer program on, you write a little shell around the evolutionary computing part of it that says, okay, you know, pick a whole bunch of problems, go to the internet, look around for things people haven't figured out, pick a whole bunch of problems, evolve some solutions to this, and submit the patents automatically. Okay? And you come back in 2 years and this machine has filed patents. You know, who has the right to the patent? Well, you've dealt with this with patentable plants and animals and whatnot. So I think the Bicentennial Man story is being played out right now, but not in the way it was portrayed in the film, if you follow me. I don't know if that helped. Okay. Well, thank you very much for letting me talk.